This is a lesson video to go along with 5-6 related rates. It's the video for example number 3, so in case you either weren't in class or needed to hear it again or wanted to go through it again. You have all the information, and I checked my units to make sure that nothing disagrees, that I don't have feet versus inches or minutes versus seconds, and I would take care of any converting then. I started to label my picture, and what I realized is the water is going to fill this cone, and it's going to be a cone of water every time, but it won't necessarily be the full 5 feet radius and the 10 feet height. But what I do know as I'm filling this in is that each time that water is in the cone and fills to a different height, its height and radius will be similar to the 5 by 10 radius and height that the cone is in shape. So therefore, I do know that my radius is always going to be half my height, or that my height is always going to be twice my radius. So there's that similarity going there. What needs to be found? I need to find the change in height as a function of time, the rate of change, but only at a specific instance. At a time when the height's exactly 6 feet. So that's going to be one specific instance as this water is flowing into the cone. So I want to decide what's fixed and what I actually know only at that specific point in time. What's fixed in the information that they gave me is that water's running in, so that would mean the rate at my volume changing over time. The water's running in at 9 cubic feet per minute, and that will be a constant throughout the entire situation. But what's only at that specific point in time is that the height of the cone of water at that instance in time will need to be 6 feet. And going back to the idea that that will be a similar cone of water, then my radius at that exact time will be 3 feet. So as the radius and height are changing, I do know that they'll change in that specific ratio. So I need an equation that relates all of these variables. So I'm going to start off with volume formula for a cone. It's 1/3. Area of the base, which would be pi r squared times the height. We have 3 variables in here, which means this is a little more complicated than the 2 variable ones we've done so far. So as I go through and look at the information that I have, I'm going to take my derivative, dv dt, derivative of volume or rate of change of volume with respect to time. I'm going to treat this as product rule that it should be. I'm going to keep that as my entire first term. So my entire first term multiplied by the derivative of my second would be a 1 dh dt. Plus, and then it would be my derivative of my first term, so 2/3 pi r times dr dt times my second term, which is h. And that's got a lot of stuff in it. That's a lot of unknowns or things to solve for and do something with, and we'll be able to handle that. Now that I'm going to fill in sub and solve, as I like to say, I'm going to sub in some known values. I may have to go back and find a few more. Keep that in mind, but don't get discouraged. I do know dv dt is 9. And at that exact instance in time that we're looking at, radius is 3. dh dt is what I'm trying to find in the first place, so that one's okay to leave in there. That is my unknown or my variable. Plus 2/3 pi, at that exact instance in time, radius is 3. I need dr dt. I don't have that one at the moment, so I'm going to have to go back and find that. I do know the height will be 6, so I'm going to put that in for h, but I've got to go back and find that dr dt. I need that. So if I back up to information that I have and that I know, I'm going to go back up to my draw and label step. I happen to know that the height will always be twice the radius for that particular cone of water. So I'm going to come and do my derivative on each side of this. dh dt will always be twice, and r's derivative would be 1, dr dt. How the height is changing will always be twice how the radius is changing. Using that information now, I can come down and for my dr dt, I can fill in some information. So for dr dt, I can put in that that's going to be half dh dt, because that is the relationship between the two. I don't mind having an extra dH/dt in my algebra because that's the thing I'm looking for. So I'll be able to factor that out and actually solve for that. So I really have two terms in here. It looks like a lot. I have this plus this, and they both have a dH/dt in them. So what I'm going to do is just pull that dH/dt out front as a factor, and then simplify each term as much as I can. 1/3 times 9 pi will be a 3 pi. 2/3 pi times 3 is 2 pi, times 6, 12 pi, times half, 6 pi. So that's really 9 pi that I need to divide on both sides in order to get my dH/dt alone. So it's going to be 9 divided by 9 pi, which in exact terms will be 1/pi. And if you went ahead and calculated a decimal value, there it is. Now I want to go back and be sure that I actually answered the question that I was asked to. So in my label and go back and get everything. Answer the question. The question initially was, how fast is the water level rising when the water's 6 feet deep? So when the height is 6 feet, water level, and we did get a positive rate here, so the water is rising, at 0.318. Here's where we need labels, so we've got to go back and see water height is a feet measurement per minute.